Okay, thank you, Chairman, for your kind introduction. So first of all, I would like to thank the organizer and the program committee for giving me a great opportunity to talk here today. So yeah, this is the first time to come to join this IEEE sensor, so I'm very excited to join this conference. Okay, so yeah, today's my title is a recent progress of flexible optical sensor for biomedical sensing. So actually, currently our group is focusing to develop the flexible optical sensor. So today I want to share our recent activity. Okay, as you know, the flexible electronics is one of the interesting devices due to the flexibility and the softness. So yeah, currently many research group and company try to develop the flexible electronics. So one of the application of flexible electronics is a display. So you know that many companies try to make a bendable display or rollable display. And another important application is a large area sensor or skin sensor because flexible electronics has a very good flexibility and material is very soft. So it means that this is very easy to attach the device to the skin. So many groups reported that this kind of skin sensor using the flexible electronics technology. So using this kind of sensor, so one of the sensor can detect the physical property of the skin. And also, of course, we can detect the chemical from the sweat or tear using this kind of sensor. And today, I want to focus to explain that this kind of flexible optical sensor for the biomedical application. Okay, so why the optical sensor is very important? So yeah, one of the important application, I already explained the flexible display. So many companies try to develop this kind of display using the organic light emitting diode. And another important application is such kind of large area organic solar cell. So because this kind of device can be fabricated by the printing method, so we can easily make this kind of large area devices on the flexible substrate. And another important application of the optical devices is this kind of flexible sensor. So if we combine the light source and the photodetector, we can detect many kind of biosignal from the inside of the body. And these devices is a pulse wave signals monitoring sensor. So they integrated the OLED and the organic photodetector to detect the signal. And also another important application is this kind of flexible image sensor. So if we make the high resolution, the high performance of the device on the flexible substrate, we can take the image. Okay, first I want to explain the photonic sensor. So yeah, from the 2014, so many groups try to develop this kind of flexible optical photonic sensor to detect the biosignal. So this is an example of the organic photonic sensors. So they fabricate this kind of pulse oximetry by integrated two colors, organic light emitting diode and organic photodetector. And another interesting application is this kind of muscle sensor. So they integrated the one light source and the four organic photodetector. Then they detect the movement of the muscle. And also they demonstrate to control this kind of robotic arm using this kind of system. But one of the biggest problem of this kind of sensor is the flexibility. So you can see, so this paper uses this kind of glass substrate devices. So it means that there's no flexibility. So it is important to improve the flexibility of this kind of photonic sensor to detect biosignal with high accuracy. Okay, so I think that many audience know that this very famous paper, epidermal electronics. So Professor Dae-Hyun Kim and Professor John Rogers reported that this kind of epidermal electronics. They succeeded to make the electrical circuit on this kind of flexible substrate. So this kind of sensor shows a very good conformability to the skin. So how they achieved this kind of sensor? So this is a very simple strategy. So you know this is the picture of the device and such kind of artificial skin. So they attach this kind of device to the artificial skin, and they check the gap between the device and the artificial skin. So you can see that if the thickness of the device is a 500 micron or 100 micron, you can see that there is a gap between the device and this kind of surface of the artificial skin. But if we reduce the thickness of the device is easily attached to the complicated structure of the surface. So you can see that if the thickness is only 5 micron, the device is attached to the surface of the artificial skin. So it means that it is very important to reduce the device thickness to improve the conformability. So our group tried to reduce the thickness of the optical devices. So this is a picture of the ultra-flexible organic light emitting diode. We succeeded to make this kind of OLED on the ultra-flexible substrate. So ultra-flexible substrate means that the thickness of the substrate is only 1 micron. So then we fabricated the OLED and we formed the passivation layer. The total thickness of the device is only 2 micron. And the brightness is about 50,000 candela per square meter. And also the EQE value of this OLED is 5%. This value is compatible with the glass substrate devices. So you can see that this device shows a very good flexibility. So we attach the device on this kind of 100 micron thick plate, but there is no degradation. Okay, then I want to explain the structure of the ultra-flexible OLED. The structure is very simple. So structure is, each layer is almost same as a common OLED structure. But one of the important points is this kind of planarization layer. And normally this kind of ultra-flexible substrate shows a very high rough surface. So to make this kind of diode structure, so it is very important to reduce the surface roughness. So we formed this kind of planarization layer to reduce the surface roughness. And then we fabricated the OLED, and finally we formed the passivation layer. So this is a picture of the real devices. So to use our ultra-flexible OLED, so we have to release the device from this kind of supporting substrate. Because this kind of very thin devices is little difficult to handle. So first we use this kind of supporting substrate to make the devices. Okay, and I want to explain the electrical characteristics of the ultra-flexible OLED. So left graph is a spectrum characteristics of the ultra-flexible OLED. So you can see that we can fabricate 3 colors OLED by changing the emitting layer. And also the right graph is EQE characteristics, EQE performance of the ultra-flexible OLED. So you can see that our device shows a very good EQE characteristics. And this is one of the demonstration of the ultra-flexible devices. So we fabricated this kind of 7-segment display, and we attach the device directly onto the skin. So you can see that, yeah, our device shows a good conformability to the skin. Okay, then we try to improve, integrated the 2 OLED and 1 organic photodetector to make the flexible pulse oximetry. So this is a red OLED and this is a green OLED, and also this part is an organic photodetector. So we integrated 3 components to make this kind of system. And the right graph shows a pulse wave signal by measuring the organic photodetector and the 2 colors OLED. So you can see that if we change the color of the OLED from the green and red, the amplitude of the pulse wave signal is dramatically changed. So from this kind of difference, we can estimate the blood oxygen level. Okay, also our flexible sensor shows a good conformability. So it means that we can easily attach the device to the skin. And also we can detect this kind of stable PPG signal using our device. And one of the biggest problem of this kind of ultra flexible device is the lifetime of the device, because normally organic light emitting diode doesn't show the good stability without a good passivation layer. So it means that we have to improve the barrier property of the passivation ultra flexible passivation layer and the substrate. So in this study, we use this kind of 5 layers encapsulation layer to improve the barrier property. And finally, we succeed to measure the PPG signal for the 5 days. So it is enough lifetime for the disposable devices, I think. Okay, and another interesting application is the blood pressure estimation. So if we measure the PPG signal and the ECG signal, we can estimate the blood pressure level. So we can calculate the pulse transition time from the PPG signal and ECG signal. From using this kind of equation, we can estimate the blood pressure level. So we measure the blood pressure and this kind of PTT, pulse transit time. And you can see that these two components show the good relationship. So we can estimate the blood pressure level from the PPG and the ECG signal. Okay, and then I want to move to the image sensor part. So currently, many groups try to develop the image sensor to monitor many kind of biosignal, such as a fingerprint and this kind of palm print. So they fabricated the high-resolution image sensor on the flexible substrate or rubber substrate. So if we make the large area devices, we can detect this kind of palm print imaging. But one of the biggest remaining issue of this kind of flexible image sensor is readout speed. Because normally we only take the high resolution image, so it means that high readout speed is not necessary to for this kind of application. But if we take the time series image, so we can extract the many kind of information from the time series image. So we trying to develop the flexible image sensor with high readout speed. So currently we succeed to develop this kind of conformable image sensor. So you can see this is a real picture of our image sensor. The total thickness of the sensor is 50 micron. And the resolution is 580 dpi. So it means that one cell size is 50 micron by 50 micron. And also the reading out speed is not fast, but 41 frames per second is enough value to detect the PPG signal. And also our image sensor shows a good sensitivity in the near infrared light region. Okay, then I want to explain the device structure of our conformable image sensor. So this is a real image of the one cell. So this is the transistors part, and we fabricated the organic photodetector on the TFT backplane. So this is the real image of the image sensor. So this is a cross-sectional image of our image sensor. So you can see we fabricated the low temperature polysilicon TFT backplane. Then we directly fabricated the organic photodetector on the LTPS TFT backplane. Okay, and first I want to explain the characteristics of the organic photodetector. So to characterize the organic photodetector, we fabricated this kind of flexible organic photodetector. So substrate is a polylane, is one of the polymer, and then we form the transparent electrode. So this time we use ITO as a transparent electrode. Then we form the electron transport layer and the active layer by spin coating method. So in the case of active layer, so we mix the two materials, PMD PP3T and the PCBM, to make the bulk heterojunction structure. And finally, we form the whole transport layer and anode by the thermal evaporation system. Okay, and this is the characteristics of organic photodetector. So left graph is the JV characteristics of organic photodetector. So you can see the black line and red line represents the dark current and the photocurrent of our devices. So you can see that our organic photodetector shows a very good, very low dark current. And also, if we irradiated the sensor by the 850 nanometers wavelength light, so photocurrent is dramatically increased like this. So from this JV curve, we calculated the EQE value. So right graph is the EQE value of our devices. So you can see our image sense, our photodetector shows a high EQE value from the visible light to the near infrared light region. So using this, also our photodetector shows a very good stability. So we check the mechanical durability and the air stability of our devices. So left graph is the bending test result. So we use this kind of very small, very thin bar, and we put the sensor and check the bending mechanical durability. So the width of the bar is about 2 millimeter. And after 500 cycles, so we check the JV characteristics. So you can see the black line is the initial state, and the red line represents the JV characteristics after 500 cycles. So you can see the JV characteristics is almost same before and after bending test. So it means that our device shows a good mechanical durability. And also right graph is the stability of the device. So we measure the photocurrent and dark current for about 70 days, and you can see the photocurrent is almost constant, and dark current is a little fluctuated, but almost constant for 70 days. Okay, then we integrated the organic photodetector to the low temperature polysilicon TFTs. So this is the characteristics of the low temperature polysilicon TFT. So we can fabricate a P-type and N-channel N-type TFT using the low temperature polysilicon. And so you can see the mobility is about the 40 square centimeter per volt second, and also the dark off current is very small, less than the 1 picoampere. And why this kind of low temperature polysilicon TFT is important to make the image sensor? So we simply check the simulated response time of the waveform. So if we use the low mobilities of TFT, the response time is very small. So blue line, aqua blue is TFT mobility is 1 square centimeter per volt second, and this blue line is 5 square centimeter per volt second. So first, we want to use the organic TFT to make the image sensor, but the typical mobility of the organic TFT is about 1 square centimeter. So this mobility is not enough to achieve the high response time. So you can see the 10 square centimeter is not enough. So if the mobility is over 40 square centimeter, the response time is less than 1 microsecond. So this 1 microsecond response time is very important to enhance the response speed of the image sensor. So we choose the low temperature polysilicon TFT. Okay, then we check the mechanical durability of the image sensor. So actually we use a low temperature polysilicon TFT, so I don't know the mechanical durability is good or not, bad or not good. So we check the mechanical durability. So x-axis is the bending radius, so we bend the device from the 45 millimeter to the 5 millimeter bending radius. So you can see this y-axis is the output signal. We change the light intensity from the 0 to the 50 micron watt. So you can see the output signal is almost constant after bend 5 millimeter. So it means our device shows a good mechanical durability. Also, we check the device itself after bending. So you can see there is no crack. And also there is no delamination between the two layers. So this is before bending and this is after bending. So yeah, our device is shows a very good mechanical durability. Okay, using this kind of image sensor, we try to take the image of the fingerprint first. So this is a measurement setup. So we directly touch the finger to the component of our image sensor. And then we use this kind of light source to take the image. So left picture is a real image of the fingerprint. So you can see we can take this kind of high resolution image using our conformable image sensor. And also another important point, readout speed is very fast. So it means that we can take this kind of PPG signal simultaneously. So we can take the fingerprint image and the pulse wave signal simultaneously. It is very important for the wearable device application. Okay, and also our device shows a good sensitivity in near infrared light. So it means that we can take this kind of vein shape using the optical components and lens and light source, and also that we need this kind of near infrared filter. So you can see the left picture is a image taken by our image sensor, and right picture was taken by a CMOS sensor. So you can see we can take this kind of real high resolution vein shape by our image sensor. But one of the biggest problems, so we need this kind of optical component to take this kind of vein image. So it is not good for the wearable devices. So next, we try to make this kind of wearable type image sensor by integrated image sensor and this kind of micro LED and this kind of flexible louver. I want to show the result of the image. So using this kind of wearable type image sensor, so we succeed to take the image of the vein. This is the shape of the vein. So you can see so now the resolution is not good. So I want to show the demonstration movie. So this is the demonstration movie of our image sensor. So here is the image sensor, and this is a fingerprint image. So for the privacy reason, the center part have been modified. So, but if you check this edge of the fingerprint, so we can clearly achieve the image of the fingerprint. And also we can take this kind of PPG signal simultaneously. Then we will take the vein shape image by the wearable type image sensor. This is a wearable type image sensor. So we directly attach the image sensor to the skin. So now the readout circuit is very large. So the system itself is very large, but now we try to reduce the size of the readout circuit. So you can see this is a vein. So we can achieve this kind of real-time vein imaging using this kind of wearable type sensor. Okay, and finally, I want to explain the analysis method. So we can take the time series image. So this kind of image contains a lot of information. So to analyze the data, so we use this kind of singular value decomposition method to extract the feature of the signal. So first we prepare this kind of 1,000 frames image. Then we use this kind of SVD method. So today I will skip the detail of the analysis method, but if we use this kind of method, we can extract the very interesting biosignal. So first, this red represents the PPG signal, and this orange line represents the breeze rate. Okay, and also we can take we can extract the blood flow mapping from the real image. So this is a real image after analysis method. After doing the analysis method, we can take this kind of blood flow imaging. And also using the SVD method, we can reduce the noise level. So blue line is a low signal, and red line is a processed signal. Okay, and also we check the blood flow imaging using the fingertip. So you can see normally the blood flow direction is like this. So if we check this part and this part and this part, the blood flow is gradually moved. Blood is gradually moved from bottom to the top, like this. So it means, yeah, this result is compatible with this blood flow direction. So maybe we can succeed to take the blood flow imaging using our flexible image sensor system. Okay, this is a summary of my presentation. We succeed to make the conformal image sensor and succeed to detect the vein shape and fingerprint image. And this is acknowledgement of my research. So thank you very much for your kind attention.